So I'm Palmer. I run the software team at SiFive. I'm here to talk about SiFive's trusted execution reference platform. And I'm also, there we go, clicks. OK, good. I've been working on RISC-V software for a few years now. I started when I was a student at Berkeley, and we had almost nothing. Right? And we've been growing the ecosystem for maybe 5 or 8 or so years. And over the last year in particular, we've made a lot of progress. We've gotten the ports of really the core components of the RISC-V ecosystem upstream. Right? And they're in pretty good shape. Right? Things like the toolchain, binutils, GCC. You don't find a lot of bugs in them. Right? Linux is upstream, boots on QEMU, all that sort of stuff. It's really getting to the point where you can actually use RISC-V to build something interesting. Right? And that will continue to grow over the next few years. A year ago, I was getting asked a bunch of questions, sort of, how do you get maybe 1.8 DMIPS per megahertz on Drystone? Right? Now things are in a lot better shape. And one of the good things is that people are doing interesting stuff, but one of the bad things is that people start asking scarier questions. Right? So questions about security-related things. Right? And this is a place where I'm not really an expert. I'm not an expert at all. That's true of most of the things that I do. But it is something that's very important. And this is one of those cases where it's really important to get out ahead of the curve. Because if we don't get everything kind of going, we're not going to be in good shape when people are building things. And we're going to end up where everybody else did, which is not where we want to be. Right? So really what we need to do is find a way to come together and figure out how to build secure systems on RISC-V. And that's what I'm here to get everyone to do today. One of the issues about security is that it means lots of different things to different people. Right? So some people want, say, a secure boot system, right? Where the owner, maybe the person who sits in front of it, maybe not the person who sits in front of it, has some amount of control over what executes on the machine. Right? These are secure boot systems. You see these are common in lots of platforms today. Right? It might mean that you have private storage. Maybe you have some sort of crypto plug-in key that holds your GPG keys, and no one else can be able to read that. Right? It might mean that you have some sort of tamper-evidence system where you don't really care if people can read it. You just need to know if they've written it. It's kind of different than it being private, but another important use case. There might be some notion of remote trust in a platform, remote attestation, right? Where you need to say, this is a machine that I know, it's not about trusting a machine that I own, it's about trusting a machine that someone else owns. Maybe you want to go, push your data to the cloud and do some compute there. And of course, the big hot thing today is side channel attacks, particularly speculative side channel attacks, right? Which I'm going to try to avoid talking about too much so I don't get into too much trouble. But they are a very important thing to worry about. What we want to try to answer here is, can we provide RISC-V systems that can actually act in a secure manner? Right? Basically, can we do this? Right? What do you actually need to build one of these secure systems? Right? What you need depends on the application and depends on the threat models. Right? So it's important to understand all these components in order to do something. Right? Initially, how do we know we have all the components we need? Right? This is not something you can just sit down and examine once. Everybody needs to agree on it and agree on that you have all the things you need to start various use cases for various threat models. And so I thought what I'd do here is just talk about what we have now in RISC-V, because we have some of the components necessary to build secure systems, but we don't have all of them. So let's go through what we have in the ISA. So RISC-V ISA has 3 privilege modes. It looks pretty standard. We have a user mode, which is where most of the code runs. We have a supervisor mode, which is where an operating system like Linux would run. And we have machine mode, which is meant for firmwares, right? Either trusted firmwares or untrusted firmwares, like they usually run now. Right? There are basically 2 protection boundaries. One protection boundary is between user mode and everything below it, and that's enforced with a paging scheme. Paging scheme looks very normal. I'll talk about it for a minute. And then additionally, we have a protection mode that's below all of this called PMP. And PMP is physical memory protection. It underlies all of the protection modes, and it allows you to block off accesses for various regions. So the address translation protection mode, which is paging, which is the only defined one. Right? It's very standard looking, 4K pages, all that sort of stuff. Physical memory protection is a base and bound based scheme. There's no translation, it's only protection, which makes it a little faster and lighter way to implement. It protects all accesses, right? So even machine mode accesses can be protected by PMPs. Right? So we'll talk about paging for a minute. Paging looks pretty normal, sits between user mode and supervisor mode. We have a CSR, per heart context, page tables, normal looking stuff. The scheme's designed to look as normal as possible. No inverse page tables, nothing super weird. We have 4K pages for 64-bit systems. Looks like everything else. There are various larger pages, access, granularity, bits, that sort of thing. It's really designed to support standard Unix systems and the protections that they need between user space and the kernel. Right? It's got supports for various extensions to do lighter weight things as well, but none of those are defined yet. The more interesting thing here is what we're going to focus on is the PMPs, because that's what's going to be used by trusted firmwares. And PMPs are also a little different than whatever people have. So for PMPs, we have PMP CSRs. They're also a per-heart protection context. Right? So each RISC-V hardware thread has its own protection context. They protect all accesses. Right? So they protect user accesses post-translation. They're physical only. They protect supervisor accesses, again, post-translation, because they're physical protection. And they also can be used to protect machine mode accesses, which default to being permissive, but can be blocked off. Right? The scheme's region-based, so a base and bounds thing with some complicated encoding of the base and bounds in order to fit useful, useful ways in which you might want to encode those regions. And you can have up to 16 of them per heart. These are all software configurable. This is a place we differ from something like TrustZone, where you can write all of these at runtime. So you can write them, turn them on and off, change the region sizes, move them around. You can use that to do time multiplexing. But then additionally, there's a lock bit. So you can lock these off until the system resets, and that can be used to protect early boot machine mode resources from later on in the boot process. It's actually chain moding machine mode stuff. And that locking mechanism also allows you to protect machine mode accesses. Right? So machine mode itself can never disable them. So we'll go a little bit how they're used. Right? You might have a system where you have two software contexts, two threads being time multiplexed onto a single RISC-V heart. So in this case, maybe you have a USB stack. USB stack's likely to have buffer overflows because they tend to have buffer overflows. And you have some crypto stuff. Maybe that's got your private keys and whatnot, and you don't want that to get buffer overflowed into. Right? So we go drop some memory, spread it throughout the system for the USB stack. Right? And then also we have different memory spread throughout the system for the crypto stack. It's an embedded system. You want to pack everything close together. You've got a couple of regions, all that sort of thing. You can set up PMPs to describe the protection boundaries of this system. So we can zoom in on one of them here. Right? So just one protection boundary. You can have up to 16 of these. Right? The USB stack can then be given a fairly fine granularity subset of the system memory, right? Where you can allocate things like buffers. Right? And if you start running some code that's buggy and is likely to have a buffer overflow, eventually, goes past the end of the stack. Without PMPs, right, you'll be able to access that. With PMPs, you won't be able to access that. And this is a key building block of being able to build a secure system. You can basically enforce in hardware privilege boundaries for untrusted user code. Examples of what you can do with PMPs, because there are lots of things you can do with these, but you can't do everything. Right? So you can time multiplex multiple programs without paging. So PMPs exist even with only machine mode and are more useful with machine and user mode. So you don't need supervisor mode in order to time multiplex protected code. You don't get translation, so you need to link that code to different addresses and whatnot. But you do get protection. Additionally, you can use it to protect devices from untrusted programs, supervisor mode or user mode, depending on the system. Right? Because the PMPs protect all physical address regions. They don't really care if it's memory or if it's a device, and you can protect things at fairly fine granularity. Additionally, you can protect and share memory in multi-CPU programs. So these are per heart regions. So that allows you to divide the address space up into distinct, per software thread regions, and then some shared memory regions if you want to do shared memory communication between them. So it can be important in a high-speed shared memory communicating system. Right, so you can also disable devices until reboot. If you have some sort of device that might only want to be accessed early in boot, some sort of trusted boot thing, PMPs can then be locked to disable access to that even from machine mode. So you can then load another machine mode bootloader later on in the system, and it can never get access to the protected regions. And these also provide some degree of protection, only the locked forward protection, for machine mode only implementations. They're really a lot more useful if you have user mode, because then you can swap them out. PMPs apply to RISC-V hearts only, so only accesses from the CPU. They allow you to protect devices by address, that sort of thing. So here's an example system where we might have trusted firmware running in one context, something like Linux, which is untrusted running in another context. Right? You want the trusted firmware to be able to do something like access the fingerprint reader, right? But you don't want Linux to be able to access the fingerprint reader. You can configure PMPs in order to set the system up. Right? Linux's accesses to a fingerprint reader will be rejected by its address space, but it can go access memory and all that sort of thing. Right? So the issue here comes in when you have a more complicated system. Right? Frequently, there are non-RISC-V masters on a bus. Right? In this case, something like GPU, which tends to have lots of bugs in its driver and have to do a lot of high-speed memory accesses. So in this case, it may be possible to ask the GPU to go across the bus and write to something you don't want it to write to. Right? PMPs can't solve this because PMPs are a RISC-V heart-specific context. So actually at SiFive, we have something called Gaskets, which are effectively memory-mapped PMPs for the other bus masters. This is not a RISC-V specification. We've done it at SiFive. We've got it on the FU540C00. That's the chip that's on the Hi-5 Unleashed. And we've had some people use this as example security monitors. We'll talk about that in a minute. So this is one of the examples of something that we'd add in a RISC-V trusted platform specification. So we have some mechanisms, some hardware mechanisms that allow us to limit the trust that's been placed on various software that runs in the stack. Right? But at some point, you do have to have a piece of trusted software. And this can, in RISC-V case, it'd be a piece of machine mode trusted software. And in order to really do anything meaningful here, you have to have some hardware root of trust. Right? So there's been a paper out, Sanctum, which demonstrates that with the PUF, physically unclonable function, you can basically build a hardware root of trust from that. So this lets you generate per-device cryptographic keys, right? It lets you ensure that you can't clone the physical devices, this sort of stuff. And on top of that, with the few other additions that are already in RISC-V, you can do things like build secure enclaves, do remote attestation, all that sort of good stuff. That paper on it's pretty good. So this is a widget that has to be implemented in hardware. And we'll need some sort of thing like this for a RISC-V secure platform specification. So additionally, a lot of threat models are involved in protection against physical attacks. Right? Things like reset timing attacks, brownouts, clock attacks, that sort of stuff. These sort of things, they're harder to solve at the software level. So I'm not sure how they would go into a trusted platform specification. Right? It's might be more of an implementation issue that you have to kind of deal with. What I think we need to do is get ahead of the curve and start writing a trusted reference platform specification. So the idea here is that we have RISC-V, the ISA. The ISA defines some security-related mechanisms. But when you write a runtime, you tend to spend more time worrying about the platform than you do worrying about the ISA. You tend to have a compiler and whatnot done by that point. So without a specification for the platform, there's no way to write portable software for that platform. Every vendor will have their own software. And that's what happens a lot of the time. That's something I'd like to avoid if at all possible. So here you'll have to specify some ISA-related concerns. There are some ISA mechanisms that are necessary in order to write reasonable, trusted, or secure systems. Right? In this case, having user mode is something that'll be mandated, existence and count of PMPs, right? And possibly some mechanism for resistance to speculative side channel attacks. But there are a lot of platform-related concerns, which are basically all the things that are memory mapped around the system. Right? Gaskets and bus blockers in order to disable various devices. Right? A mechanism for resetting, a reset sequence that everyone can agree on to do secure boot. Right? And some mechanism for describing and detecting the various hardware mechanisms that are around the system. Maybe a PUF, maybe crypto devices, all that sort of stuff. So basically, ISA specs aren't really sufficient to do the whole system. We need a platform spec. That currently doesn't exist, so we should all get together and try to write a platform spec that we can all agree on. Our goal at SiFive is to build a trusted firmware that's an example of how to use this platform spec on our systems. So it'd be very simple, static partitioning for multiple security zones, right? And so no time multiplexing, right? Here it'd be a way to evaluate the trusted platform spec. So we design it to be simple and portable. So we'll use, for example, other people building proper platform specs, right? Usable in simple systems if you don't need to do time multiplexing or anything like that. Nice proof of concept to make sure it works. So other people are already, without a platform spec, working on more interesting security monitors. Berkeley has a talk in about an hour, I think here. It's got some active research in security monitors. And the code they have runs on SiFive's chip. Again, part of the reason we need a spec, so it would run on everyone's chip. And then HexVive also has a security monitor. We have a demo downstairs, and that's a commercial implementation. We have a third demo downstairs of some SiFive-related crypto IP. SiFive has our Freedom U54 core IP. That's the same one that's on the ASIC. We've integrated that on an FPGA with Rambus's crypto manager, which provides a definition of a secure boot reset sequence, some crypto accelerators, things like puffs. And we have a demo downstairs running, doing secure boot on Linux-based RISC-V system. Right? So you can insert an SD card, and if the SD card is signed correctly, it'll boot. If it's not signed correctly, it won't boot. And that is the extent of my talk.